Good afternoon and good evening to those of you in Europe, and good morning to those of you in Australia. Welcome to session 3 of the ESIG 2021 Meteorology and Market Design for Grid Services workshop on the topic of probabilistic forecasts and their use in operations. I'm Charlie Smith, the Executive Director of ESIG, and I'll provide a few brief opening remarks. As I think you know by now, our workshop sessions are all being held online and are open to everyone. And I do want to let you know that we are planning our first major in-person event since the COVID outbreak last year with the Fall Technical Workshop in Austin, Texas, during the week of October 25th. Please mark your calendars and look for additional information in the near future. This workshop was planned with the input of our ESIG Offerings Committee, chaired by Bethany Frew of NREL and Julia Matoivasan of ERCOT. The committee consists of the chairs of our 6 working groups and several of our board members. We have a great set of volunteers who really make ESIG what it is, and we encourage you to become involved if you're not already. You can find us on the web at esig.energy, send an email to info@esig.energy to get our monthly newsletter, and follow our activities on LinkedIn, Facebook, and Twitter. ESIG also serves a leadership role in the Global Power System Transformation Consortium, often called GPST, whose mission is to bring together key actors from around the world to catalyze a rapid, clean energy transition at unprecedented scope and scale. ESIG leads one of the 5 pillars that deals with the research agenda for the system operators. More information on GPST can be found at www.globalpst.org. Regarding logistics for today, I would ask you to note that session 3 will be 2 hours long. We had a lot of feedback that our 1-hour workshop sessions were too rushed, so we've moved to some longer formats for this workshop. We'll have a number of individual presentations of approximately 15 minutes each in the first part of the session, followed by 30 minutes of discussion and Q&A after the last speaker. As we're doing with all of our webinars now, we'll be using the Slido platform for managing the Q&A. You should go to slido.com on your device and enter ESIG8 as the event code to ask your questions. Please be sure to indicate the person to whom you're addressing the question. The instructions are also at the bottom of the background slide for the webinar, and you'll be reminded by the session chair. You'll see a thumbs up button next to the question on Slido to allow you to vote on prioritizing the questions submitted. But please keep the questions coming during the presentations, and we'll address them at the end. We will follow up with written answers to any questions we don't get to during the Q&A. Recognizing the limitations of a webinar with more than 100 people on the lines will be muted. So again, we ask you to use the Slido platform to ask your questions with ESIG8 as the event code. Today's session is titled Probabilistic Forecasting, State of the Art, and Use in Operations. We have a great lineup with practitioners from Europe and the US who will be speaking, and I'm looking forward to a really great session. The session was organized and will be chaired by Ben Hobbs of Johns Hopkins University and Aidan Tuohy of EPRI as co-chair. Ben is a professor at Johns Hopkins and the chair of the CalISO Market Surveillance Committee. Aidan is a manager at EPRI and the chair of our System Operations and Market Design Working Group. Both Ben and Aidan are familiar faces at ESIG and bring a lot of good experience and insight. They're both good friends and good friends of ESIG, and I'm very happy that they're able to be here with us today. Ben and Aidan, we appreciate your participation, and I'll now turn it over to you, Ben.
Okay, thank you, Charlie. It's an honor to be asked to organize this session, and also an honor to be called a friend of ESIG and a friend of you. This has been a strange year, but we have learned that this can be a very effective way to get information from the best people around the world to users, potentially users all around the world. And it will be interesting to see how ESIG's formats evolve in the future to both take advantage of this capability, but also to get us back together for the fellowship and personal interaction that we miss so much. So today's session is a mix of a broad overview, which you'll hear from Pierre, of what is new and in terms of technology, and what is new in terms of uses of probabilistic forecasts. So Pierre will be kicking us off, and then we'll do some deep dives. Daniel and Carlo will be talking about particular probabilistic forecasting systems and some technical features involved in each and some of their new features. And then Corinna and Bri-Mathias will be talking about advanced uses of probabilistic forecasts to improve the cost performance, reliability, and I hope sustainability of electric power systems. So I would like to start by introducing Pierre, and I'll remind everybody that we're going to go with 15 minutes for each talk, and between talks we'll have a quick introduction of each of the speakers, and then we'll have the questions and panel discussion at the end. So please put your questions into Slido as Charlie discussed. So I'm very pleased to welcome Pierre Pinson. He's a professor of operations research at the Technical University of Denmark, also an IEEE fellow and editor-in-chief of the world's leading journal of forecasting called the International Journal of Forecasting. He's made many contributions, not just to forecasting, but to fundamental optimization methods, as well as simulation of power markets and energy systems. So Pierre, thank you for joining us today.
Thank you very much. It's my time to share my slides and to talk to you. It's a pleasure to be invited for this event, and I see there are many participants, so it's even more of a pleasure that we do that for a broad audience. What I'm supposed to do here today is to give a talk that is more of an overview and introductory, and I can see you have many very good talks afterwards that are going to go deep diving into some of these topics, right? The machinery for probabilistic forecasting, how they are used, etc. So the reason why I want to give you an overview is because I think there's a lot of exciting stuff going on within probabilistic forecasting, but also I think we have to, let's say, keep our feet on the ground and really understand how we need to bridge the gap between probabilistic forecasts on the one side and the operation needs on the other side. So let's kick it off, and let's be a bit provocative to get started with. I'm often asked, actually, by students, but also by colleagues within industry, what makes a forecast probabilistic? And I think that's something maybe important to discuss to get started with, because here we've made this session about probabilistic stuff as if all of the others didn't have anything probabilistic. But at the end of the day, all the forecasts are probabilistic. And often, maybe one of the issues with our colleagues within industry that are forecast users, casual forecast users, or intensive forecast users, is that there are a bit of denial about the fact that all forecasts are probabilistic. Why do I say that? Is because we know many types of forecasts. We've been asked to develop a new type of forecast all the time. And today, I think we have pretty much good standards in terms of the most important type of forecast. And they're here in these three blocks. And on the left, you're going to say, oh, but these are not probabilistic forecasts. These are the point forecasts that we know. They are deterministic. But by definition, these point forecasts are some kind of summary statistics about some random variable we want to inform about, right? So if we say that power generation in the future is a random variable, and you might say, I don't believe that. For me, it's just something that's going to happen. But most likely, since we don't know how to model it correctly, we have insufficient information about the weather, I don't know, uncertainty about the turbines, the conversion process, etc. We have to accept this stochastic process. And these point forecasts are just giving a single value for each location, lead time of interest, etc., about what may happen, right? And then there are two types, quantile and conditional expectation that people are used to, and that's a single value. But these are not deterministic, actually, if we think of it mathematically. In the middle, we have the interval forecast, and there it's something that has been first proposed to give a feeling about the uncertainty around the point forecast that people were used to. But if you have a lot of these interval forecasts, we get these very nice pictures where we get a full description about the predictive densities, right? And these forecasts have been shown very useful in many applications for reserve requirement quantification, for trading, etc. And finally, on the right, you have these scenarios or ensemble forecast, and I'm sure some of the other speakers will discuss that. Most likely, Corinna will have stuff to say also about ensemble forecasting. And this is also something that's very nice because then we have a set of plausible features that we could use, you know, a la Monte Carlo as input to some tools for optimization, simulation, etc. And that's a very useful type of probabilistic information we can use. So this is what we're used to. And now we should move on towards the, let's say, what we need, you know, how to bridge the gap between the probabilistic forecast and the operational needs. So there I want to discuss three main points. One, it's homogenizing the state of the art, and you'll understand why I say that. Second, adapting to the operation needs. And then the final thing, I will try to argue that our biggest operational need is to get people to actually share data, and we have to find a way for the information to flow and to get the most out of it. I'll explain you that when we get there. So first of all, we need to homogenize the state of the art. And I would say, you know, the different aspects of energy forecasting have picked up at different periods in the past. So the first type of energy forecasting would be load forecasting. Already in the 70s, you know, there were papers appearing. Then wind power forecasting got very strong in the mid 90s. And now solar forecasting has picked up very strongly. And maybe one of the most important things for operational needs is actually also that we have some kind of homogeneous view of the state of the art so that you don't get, for instance, amazing forecasting products that are tailored to your needs, let's say on the load and wind side, and maybe products that are not up to speed on the solar side or price forecasting side. And I'm saying that as an example because this could be any other combination that would always be annoying. So one of the very nice things actually in terms of adapting to operational needs is that we are on very good tracks to homogenize the quality of all these forecasts, the way we communicate them, and also the bridging of the gap between the academic research, the development by vendors, and the final use of the forecast in practice. And now it's not only these, let's say, pillars of energy forecasting that we have seen so far that are very important. We see that very new type of energy forecasting are just appearing. Some people look at line rating, some people want to forecast flexibility, etc., etc. So I think there's really a lot of maturity in energy forecasting, and that's very important to adapt to the operational needs. The second thing is that we really see there's so much activity, so much momentum, that we see many good groups in the world in academia, many good vendors around the world that really go back to some of the basics. And I'm not going to say that we got our basics wrong, but I must say that we had to do a lot of development very fast, I think over the last 20 years, to adapt to the operation needs actually, and to be sure that we're able to deliver something that is usable. But we have realized that mathematically, there's much more to do. And there are important aspects in energy forecasting that we could cover much better. And I'm thinking about certain things, for instance, the fact that energy generation for wind and solar, for instance, is bounded between 0 and nominal capacity or 0 and the clear sky model. If we take that into account much more thoroughly from a mathematical point of view, we can produce much better probabilistic forecasts. And also we might actually make it, I would say, cheaper and easier to produce because we will have a stronger mathematical background. There's also aspects related to forecast verification. Forecast verification is seen as something that's very pragmatic. You know, it's almost a practitioner's problem, but actually there's a lot of mathematical aspects. When we dig into it, we realize we can learn much more about the plus and minuses of forecasting approach, especially probabilistic, that we would not if we stick to some basic scores. So there's also a lot of hope now that we can develop much further the forecast verification framework so that we improve both the models for the forecast, but also the way we can analyze forecast quality and communicate it to forecast users. So lots of challenges, but a lot of good people working on those. All right, the second thing I wanted to discuss is adapting to operational needs, like really in practice. We have to connect the forecasters and the forecast users and make sure that the products are adapted. So in that sense, we've realized actually that we could go further than these forecast types that I mentioned before. And I think we'll have some talks discussing later, you know, ramp forecasting. Some people have considered directly forecasting reserve requirements. There's been many kind of ideas related to new products. And I think that's really nice that we see today. I would not say the sky is the limit, but somehow there's such a good communication between forecasters and forecast users that we're really able to design new forecast products and tweak methodology towards that, so that we really deliver the best as input to decision making. So I have an example here. For instance, if we were to do some stochastic optimization in the sense of robust or chance constrained optimization, and we want to have information, probabilistic information as input, but in a multivariate setup. Actually, we don't want to have these predictive densities that I showed before. We don't want to have these scenarios that I showed before. What we really would like to have is some kind of polyhedra, like I show here, or some kind of ellipsoid. And that would somehow summarize what we need for the robust or the chance constraint optimization. And so I think in a way, we can look more and better into this connection between the decision problems and the type of forecast we can produce. And in most cases, it's not really, it's not trivial, but it's not extremely complicated to find a way to design forecasting products that are really adapted to the needs. So another example from some colleagues at EPFL and also Mines Paris Tech in France, they've been looking at some aggregate forecasts at distribution grid level for different types of renewable energy sources and loads, with the idea to make some aggregate flexibility forecast at the point of connection, right, with the transmission level. And that's also a point where there's quite a lot of mathematics to make sure that you have some kind of additive consistency, that you have the dependencies right between the different sources, space and time, also dependencies, and you summarize that into the top figure when you have a two-dimensional object in terms of active and reactive power, which is your forecast of the flexibility that you can provide at the connection point based on all the resources under this connection point. So there again, not trivial, but still we can do a lot of very good things that are really adapted to decision processes and really get the most out of the forecast. But then there's one very important point, which I think is what should be the key focus in the future. One of the operational needs, if we want to really improve forecasting, if we want to get the most out of all the data that we collect, is that we need to find a way to incentivize people to share data. And sharing doesn't have to be free. Sharing doesn't have to be revealing all your information, right? And many people have been discussing Google that pushed federated learning. I was reading today, everybody is blown away by DeepMind saying that PCA can be reinterpreted as a game, you know, and that you can use distributed optimization to solve it. Any kind of learning problem that we have in forecasting can also be reinterpreted as a game, and we can design a market so that all agents that contribute to improving forecast could be rewarded, or, you know, there could be some privacy preserving mechanism, etc. So that's some of the work that is being done within forecasting today, more in research mode than really ready for operation. And I hope that many groups in the world can show you more about that in the future. So I'm just going to give you a motivating example and some proof of concept. And then the example that's after, I will jump over it. You will have it in the slides, and I will conclude. So a very important and nice motivating example, I think it's participation of renewables in electricity markets, and I consider here wind farm. So if you were to consider 3 wind farms participating in the electricity market, they place their offers in advance based on forecast, and then they're going to get some form of revenue, right? But then the revenue is directly, or say, affected by the lack of forecast accuracy. So you would think they all have an interest in improving their forecast, and since they all have data that may be valuable for each other, they could just share data and then it could improve forecast. And we imagine that all could benefit from this process, maybe some less than others, but still there should be some kind of benefit from information sharing. But actually in practice, they have no interest in doing so, because some wind farms might feel they are sensors for the others, so they share information, but they get no benefit. Or some might feel, oh, I get less benefit than others, or some might feel we're in competition, so I don't want to share, right? So what should we do? We should design some kind of mechanisms so that if you want to share data, it could be against money, and we have to find the right pricing for that. And for those who don't want to share data, maybe we could do some distributed learning, and we try to do it privacy preserving. And at least I can get the value from the information you may have from my wind farm, but you will never reveal your information. And then we want some pricing involved. We want to study the properties of these markets, etc., etc. So this is a motivating real-world example, and we have so many of these examples. And my colleague Ricardo Bessa, for instance, and I often have discussion about different kind of setups around the world where there would be an easy use case so that you see a possibility to do that, right? Okay, so there are 3 types of proof of concept setup that we could consider. Collaborative analytics on the left, data markets in the middle, and analytics market on the right. So with collaborative analytics, people are ready to collaborate, but they don't want to share the data. So that's where we do distributed optimization and privacy preserving. It's already been done. I've published some papers. Some other groups have published some papers. It's not very complicated to do that. And as I said, the federated learning by Google is also one version of that, right? In the middle is data market. So in this case, people are ready to share the data, but they want to be paid for it, right? And there are some ideas out there, and we're also pushing some new ideas in this direction. It's possible to design markets for information, for data, where it will have all the nice properties. So that's what you can see by yourself in the slides that are afterwards. And on the right, what we would like to do is somehow to combine everything, to have a heterogeneous population of agents. Some may want to share, some don't want to share, some want to be paid, some don't want to be paid, some want privacy preservation, some don't care so much, etc. So that would be the Graal, the end game, right? But there's a lot of research needed for that.
So Pierre, Pierre, we're at 20 minutes now. So if you
sorry,
quickly
I'm
wrap
just
up.
going to conclude. I had my timer here. I thought I was at 15 minutes just now. Sorry for that.
Okay.
So I just wanted to conclude by saying probabilistic forecasting is a very active field of R&D, and I hope I gave you a good overview. And what's very nice today is that there's a very good communication between academia, vendors, and users. So I think there's lots of nice developments going on. So, and I think the biggest challenge that we may discuss in the panel at the end is supporting the adoption of probabilistic forecast by forecast users. Thank you very much.
Okay, Pierre, I'm sorry that we're short of time, but thank you for keeping within time.
Yeah, that's fine. That's fine.
Okay. Great. So we'll now go to our second speaker. As Pierre said, we're going to be doing a couple of deep dives, first into the technology of probabilistic forecasting and then into their uses. So our next speaker, Daniel Kirk-Davidoff, he leads Underwriter Laboratories R&D efforts for renewable generation forecasting and other grid forecasting services. Which includes, for example, satellite-based solar generation forecasting and the impact of climate change and renewable resources. Previously, he's worked on, for example, modernization plan for the Uganda National Meteorological Authority. He's investigated interactions between climate change and ozone depletion and many other geophysically related topics, including paleoclimate problems such as the Eocene polar warmth and the Messinian desiccation, which you can ask him about. So Daniel, it's all yours.
Thanks so much, Ben. Yeah, so I'm going to talk about some exploratory research of using the same kind of machine learning algorithms that we typically use for our single valued forecasts for probabilistic forecasts. And in this case, we're branching into net load forecasting rather than just generation forecasting. That's a bit of a newish thing for me, so forgive me if occasionally when the axis of the graph says net load, I slip and say generation, because we're still learning this stuff. That was a great introduction from Pierre. I really appreciate that. I think there's some fascinating stuff to be developed further in the interaction between ensemble numerical weather prediction ensembles as inputs to machine learning based probabilistic forecast schemes, and then having the output be a reasonable set of trajectories, which might not be exactly the same as what you would get by putting each numerical weather prediction model's forecast through a machine learning code and then getting a single valued prediction. There's some really interesting questions about how to tune that up to make a beautiful set of trajectories that perhaps had equal weight or something along those lines. Okay, without further ado, so I'm going to show an example of the application of XGBoost, pretty standard machine learning code, to essentially diagnosing the influence of various environmental and calendar factors on net load in 3 different grids. And I've anonymized these grids. Most of this data is public anyway, but we'll just keep it anonymous to make sure everyone's happy. So we've got grid A on the left, grid B in the center, and grid C on the right. Grid A and grid C, you can see have pretty strong seasonal cycles, but of a different quality. You can kind of see that grid A emphasizes wintertime. These are all northern hemisphere. So grid A emphasizes wintertime load. That is when you get the highest net loads. And in grid C, summertime is when you get the highest net load. And then in grid B, there's sort of a little bit of a seasonal envelope to the forecast, but you can tell that the main variability is day to day and hour to hour. Okay, so moving right along, using the right arrow. Okay, here we go. So for grid A, what we're going to do is we're going to have 3 different slides that each look a lot like this. And on the left is that same plot I showed you before. And then the right 6 figures are these Shapley diagnostics, which is a way of getting behind the black box of machine learning codes to kind of understand better through a sort of differential analysis of what each variable is contributing to the load. And the colors there have to do with, like, if on the x-axis you see one variable, the colors correspond to sort of a secondary role played by another variable in determining the output of the forecast. So for this grid A, you can see that temperature is the dominant influence on the net load. That's the top bar in the importance figure in the top center. And then hour of the day is next most important, and day of the year comes after that, and day of the week comes after that, and then maybe dew point, and then way at the bottom we have GHI as a very slight influencer on this on this electrical grid. Now for temperature, we can see a really typical nice compact curve where as temperature gets colder, the electrical load goes up, and as temperature gets warmer, the electrical load goes up also, but not very much, because this is a part of the world where it doesn't get terribly hot in the summer. And so not too many people have bothered to install air conditioning, and their load doesn't increase very much when it gets hot. In the daytime, we have higher load than in the nighttime. And in the winter time, we have higher load than in the summer, somewhat independently of the temperature impact. And so that may just be that the algorithm isn't doing a great job of separating temperature from day of the year as a predictor, but it might also be that there's an increase in, at-home activities, more lights and, I don't know, more TV watching and such during the winter. And maybe in the summer, people are leaving this market for vacation, or they're just not spending as much time indoors, not using as much electricity. And then a day of the week, we see people use a lot more electricity during the weekdays than they do on the weekends. And then we have GHI, and we see a very slight tendency towards more electrical demand when you have higher GHI. So who knows, maybe that's a little bit of an air conditioning signal in the summertime, where if you've got direct insulation on a house, that heats it up. Not quite clear. Okay, next slide. Here's grid B. We have, again, not much of a seasonal cycle, but a little bit of one, and a really strong diurnal variability. And so unsurprisingly, the very top influence on this one is hour of the day. I think it might be hidden on some of your screens. Below that is day of the year, then GHI. So this is a market where as GHI increases, so that means when the value of GHI is high, is red in this plot, the influence of GHI on the net load is negative. Okay, that's probably because there's a lot of PV panels in this market. And you can see that in the diurnal dependence of the net load as well, because in the brightest sunshine hours of the day, the load is generally depressed, whereas load reaches its peak in the evening hours. We can see there's still a temperature dependence here. It's actually dew point that gets the strongest relationship with presumably air conditioning load. As the dew point gets higher, people turn on their ACs and use more power. Weekdays are higher use than weekends. And then we have this interesting plot of GHI versus net load. And you can see that there's a difference in the slope of the curve between the morning hours and the afternoon hours. The afternoon hours, the slope is steeper, indicating maybe there's a higher fraction of west-facing solar panels in this grid. Okay, next, in our third electrical market, we've got, again, this pattern of strong seasonal variability superimposed on pretty strong diurnal variability. Again, the temperature, as in grid A, is the lead predictor of net load. Hour of the day and day of the year are the next strongest, but then GHI comes in. So here we see on the upper right figure, you can see a nice compact curve of temperature versus net load, and you can see GHI having a strong negative impact on the net load as well. And this presents the possibility that we could diagnose the amount of solar capacity in a grid by looking at the strength of this slope at different over time. So we'll see that on the next slide. So here's the same part of those charts analyzed for the year 2014 on the left and for 2020 in the center. And if you look at the numbers on the y-axis, you can see that the bottom of the GHI curve is about twice as far down in 2020 as in 2014. And when we analyze this separately for each year, you can see indeed that as we go from 2016 to 2020, there's a strong increasing trend. And if you convert these into megawatt units, it comes out to an increase from about 70 to about 150 megawatts, which is in reasonable agreement with the official capacity numbers in this particular location. I'm not making any claims to tremendous accuracy on this, but we haven't tried really hard. All I've done is train the model on the existing on all these inputs, GHI, temperature, and so on, and then perturb the GHI in the range of high GHI where the contribution to negative load maximizes. And when you look at the resulting change in net load, when you perturb the GHI by 1 watt per meter squared, it's about twice as large in 2020 as in 2014. Okay, next slide. So how does this turn into a probabilistic forecast? Well, XGBoost, as many other machine learning codes, are rooted in, they were kind of invented to solve problems like, I have a whole bunch of pictures and I want to decide which one's a cat, even though some of them are cats and some of them are dogs and some of them are ferrets. So how am I going to figure that out? So you train the algorithm, and it is well suited to come up with a probability that the data that you've supplied it indicates that it will be in one of several categories. So in this case, what we've done is instead of using a regression mode for XGBoost, we've used a categorical mode, multi-soft, and then looked at the probability that the net load will fall in 4 bins. In this case, say between, this is just a rough example, between 0 and 10, 10 and 20, 20 and 30, 30 and 40. So then, given the probabilities in each of these bins, we can sum those up and come up with a cumulative probability distribution, because what our clients are interested in is our probability of exceedance forecast, where we say how many megawatts is the level than which there's, say, an 80% chance that the true generation will exceed that level. So by interpolating this cumulative probability distribution that we get from these categorical forecast onto fixed probabilities, we can get that POE forecast. Okay, so here's an example of that. This is the rough initial forecast of the categorical probability. So you can see that, you know, the mid-range is like the 30% of the range from minimum to maximum net load are pretty frequent, make pretty frequent appearances in this as having a pretty high probability that the net load will fall into that bin, whereas the extremes are less frequent. But you can just occasionally see a situation where the maximum net load, sorry, is a plausible outcome. Okay, so once we do our interpolation trick, then we get a probabilistic net load forecast deriving from this machine learning algorithm. So why are we going through all this? The traditional way of doing this kind of a probabilistic net load forecast would be to do quantile regression on you know, a reasonably long history of forecasts. What the machine learning algorithm brings into the picture is an ability to be aware, to become aware of biases of the model. So if, you know, at some times when various features of a numerical weather prediction model take on certain values, and these may be variables in the numerical weather prediction model that are not the ones you would most obviously think of as predicting the thing that you care about. They might not be temperature, they might not be GHI, they might be some aspect of the atmosphere remote from your immediate concerns, but that aspect might be a good clue as to situations when the model would have a bias one way or the other in the variable to be predicted. And by use these machine learning codes, because they don't have any preconception of what the functional form of the relationship between one variable and the output ought to be, and can put together a bunch of different variables in these regression trees, the thought is that we're going to do a better job at having models that recognize strange cases that occur maybe 3 or 4 times in a year that lead to predictable biases. And whoops, let's see. Next slide. Okay, the reason to be very thoughtful about doing net load forecasting as opposed to doing forecasts of individual components of the net load, say the raw load and then the behind the meter solar generation, is that there may be covariances between the components of the net load. And if you just take an independent forecast, even with a probability distribution attached to it, it's hard to know how you would combine the errors of that forecast. And this slide just illustrates that depending on the time of year, the relationship, say, between GHI and temperature can be different. So in the winter, there's not a very strong relationship between GHI, that's these blue values. There's not a very strong relationship between GHI and temperature, whereas in the summer, there's a little bit more of a positive relationship. Sunnier days tend to be warmer. And we can see that on the far right plot, where we've only looked at midday data, so we're not being confused by the diurnal cycle, which of course it's warmer in the middle of the day than it is at dawn or dusk. But even if we look at midday only, there's still a bit of a correlation between GHI and temperature in one season and not so much in another, which means that the way you would combine the errors in a net load forecast ought to be different in different times of year. So it's useful to do it all in one unified system. I'm going to skip the next slide because I'm running out of time and just come to leave my conclusions up here. So our imperfect ability to forecast weather causes uncertainty in both load and sort of raw demand load and renewable generation. And as renewable generation increases as a fraction of demand, the covariance of solar radiation, wind, and weather-dependent electrical demand becomes more important in determining the load. So it's important because that since error covariance can vary by location and may vary by season, to have a consistent system to produce the overall net load forecast, which is of very strong interest if what you're trying to do is meet the difference between load, is to meet the load less the renewable generation. Okay, thank you very much for your time, and I hope I didn't go too far over.
No, Daniel, actually, that was perfect. You and Pierre were both perfect. So
okay,
we're
awesome.
Right on time, and looking forward to the discussion later on. I'm sure there'll be good questions for you. Reminder to everybody, please go to Slido and please add your questions there and rate the questions that have been put up. Okay, I'm going to introduce Carlo Siebenschuh, who is a research scientist at IBM's T.J. Watson Research Center, Yorktown Heights, New York. He has master's degrees from Karlsruhe Institute of Technology in both industrial engineering and pure math. And he will shortly have a PhD in computer science. At least he's planning to do so. We wish him luck. Or maybe we should tell you, you should run while you can. Don't make that mistake by getting a PhD. But meanwhile, at IBM, he's been working on distributed deep learning and probabilistic forecasting in finance and meteorology. And I'm pleased that he's been a colleague of mine on a solar forecasting 2 project that we've had with NREL, Hopkins, and the University of Texas, Dallas. So, Carlo, it's all yours.
Thank you so much, Ben. I appreciate the warm words. For now, I will not start running, but I do the presentation first. But I'm very honored to talk to a wide array of people who are so distinguished in the domain of probabilistic forecasting. And today I would like to present what IBM research has done in the past on probabilistic forecasting of solar power generation. So the presentation will be held by me. However, a lot of work of others went into that. For example, Hendrik Hamann, Ray Zhang, and of course, collaborators at Johns Hopkins University, NREL, and the University of Dallas in Texas. So thank you very much for that. However, I would like to add first that this work would have not been possible without the support of the US Department of Energy and their various initiatives over the past half a decade now. So tax money at work. But maybe after a year like this, we should catch up on the current state of solar power generation. So right now it amounts to about 3% of the global electricity generation. Interestingly, despite the tribulations of the past year, 260 gigawatts of capacity have been added, which is a record, mostly in Asia, that is. And going forward, growth will continue at a significant rate, namely of 20% per year for at least the next 10 years. So this is quite significant. And of course, at this point, my previous 2 speakers already introduced the importance of probabilistic forecasting on an individual level, but it plays a key role on a macroeconomic level as well. Because renewables in general, and solar forecasting, solar specifically, introduce quite some uncertainty into the network, as everyone here in this panel knows. With more and more renewables entering the network, more and more uncertainty is added, which requires a higher ramp requirement in the end for regulation. And unfortunately, it's this kind of economic force which could dampen the accelerating speed of the introduction of solar energy, which of course nobody wants to see. If we take a look across the pond, or for some of the panelists, that is just taking a look around, namely in Europe, different countries have a different degree of uncertainty through their different variations of introductions of renewables. And if solar energy, as the hardest to predict energy generation source, if that is manageable, then most likely the other renewables, namely wind, are somewhat more predictable as well. And this is exactly what the work of IBM Research with Johns Hopkins, NREL, and UTD we're trying to do. So, and it started all with the Solar Forecasting Project 1. And for that, the core idea of IBM's deterministic solar forecasting system was the following. If we take a look at the statistical accuracy plotted against the forecast horizon, we can see different methodologies result in different characteristic accuracy curves. So for example, going with persistence is very good when the forecast horizon is neglectable, but of course, accuracy drops sharply the further out we look. If we take interpolation techniques, for example, a la Lagrange, then it looks fairly well going further into the future, but naturally, a sophisticated numerical model will beat most of the time these systems in the intermediate and long run. However, in the real long run, climatology is somewhat almost unbeatable. And looking at this graph, Hendrik Hamann, Ray Zhang, thought that maybe there's a way to combine these models dynamically. And that is exactly what happened by taking insights from time series analysis, which operates in this short-term range, numerical weather prediction systems, which work for most of that forecasting horizon range, and the statistical averaging methodologies, which are applied to improve upon climatologies. The so-called Watson version 1 was born, which is a machine learning based model ensemble system, which combines all these models to provide a forecast which is fairly accurate across many different forecast horizon values. However, since all these ingredients are deterministic at their heart, of course, the output of the Watson V1 system was deterministic as well, or in terms of the nomenclature raised earlier, it was a point forecast. So, but to go from a deterministic to a probabilistic forecast, what kind of uncertainties arise? Naturally, we have a measurement, usually through a set of measurement stations, and they provide with some lag raw measurements. Through a numerical weather prediction system, of course, coarsely summarized here, we get an output which summarizes the state of the atmosphere now, as well as the state of the atmosphere in the future in terms of temperature, precipitation rate, among others. And now the statistical post-processing, in our case with the Watson system, is being applied to take the output of the NWP system to then infer the global horizontal irradiance, which can be turned into a prediction of the solar power generation. And among this value chain of data processing, there were a lot of papers and books who basically took a look at what is actually the kind of uncertainty we deal with. So for example, when it comes to measurements, there has been this paper on the truth going in and going out of numerical weather prediction systems. Naturally, NWPs are so ubiquitous and in some sense single-handedly introduced high-performance computing over the past few decades. Now people taking a look again to identify what kinds of uncertainties arise, for example, through the parametrization alone, or by moving from partial differential equations to solve initial value problems to stochastic PDEs, which are a very vibrant subdomain of pure mathematics these days, and they will invariably enter NWP research as well. And the post-processing stage has been firmly looked at for the past 20 years, namely through the introduction of strictly proper scoring rules. And we took a look at this literature and tried to merge these different kinds of uncertainties in our probabilistic forecast to properly reflect the uncertainty. And the question now is, how does the output changes when including these kinds of uncertainty? So on the left-hand side, let's imagine we want to predict the global horizontal irradiance for some place in California for April the 1st, 2020, and we do it in hindsight. Naturally, with a point forecasting system, we get this nice diurnal pattern for April the 1st of the global horizontal irradiance. That is Watson version 1. Watson version 2 now, which is a probabilistic forecasting system, provides still the nice diurnal pattern. However, it provides actual probabilistic information by means of quantiles. And in this case, it is the 5, 95, and the 25 and 75 quantile. And in red, in the middle, we see the conditional mean. So this is how the output changes. And the question now is, how does this conditional predictive distribution actually arise? And that can only be understood if we look for a moment back to the deterministic model. So just to make the legend clear, we have a current time t, we have a forecasting horizon h, we have some space variable, which sounds very mystical, but at the end of the day, it's just a pair of latitude and longitude. And most importantly, for Watson V1, we have a weather category. And this is the core to understand the whole system. On the left-hand side, we have basically a regressed variable, which is the global horizontal irradiance, looking into the future for a specific spatial location. And on the right-hand side, we have the input data coming as an output from the NWP. In between now, and apologies for the many indices, but they make a lot of sense because we basically have a function f, which represents one instance of an inference model, and it is indexed by time, space, the forecast horizon, and the weather category C. And we take basically a set of different model instances, and they are conditioned on the weather category. And the kinds of weather categories around were determined by a machine learning algorithm prior. And when the system is running, it detects the most likely current weather category in the atmosphere, and it then rebalances the weights in between this ensemble. So in some sense, Watson version 1 was a machine learned ensemble learner. So now turning this into a probabilistic setting doesn't change that much. We still have the current time, the forecast horizon, but now the weather category has disappeared because we don't want to do a prior step of categorizing the different possible states of the atmosphere, because that is just, in some sense, a superfluous step. And now, since it's probabilistic, we have the cumulative distribution function in play. So on the left-hand side, it's, first of all, it is not the value itself anymore, but we are looking at the quantile. And the quantile function, of course, is the inverse of the cumulative distribution function. On the right-hand side, the input still remains the same, which is whatever the numerical weather prediction system provides for us. And now the model instances have changed. Most notably, there is no space variable anymore. Why is that? Because this system doesn't provide the forecast for a single location, but for all locations. So the space index is not required anymore because the model is applied for the entire area of interest. And that happens through embedding learning, namely of embeddings which are parameterized by space and time. Ensemble learning is still required. So this is why we have a set of model instances which just improve the performance, which is a natural way to go. The previously mentioned XGBoost is an ensemble learning mechanism as well. This is just how the cookie crumbles these days in machine learning. And of course, we need to verify this. And how do we do that? We picked 24 reference stations across the United States. On the West Coast, where CAISO is present, in the Midwest and in the South, where MISO is present, and on the East Coast with the various system operators in New York, New Jersey, and the surrounding states. And of course, the input data is available in a rasterized fashion for the entire United States, mostly North America as well. And now we related our forecasting output with these specific stations. We thought very deeply about how to do that, because mean square error, mean absolute error, which are very popular in the deterministic forecasting scene, are really not applicable. On the other hand, if we use proper scoring rules, which are highly appropriate for probabilistic forecasting, we still have a scalar valued error metric, which doesn't provide a lot of interpretability. And we went for a metric which is based on a visual tool. So this metric provides a quantitative and a visual assessment of the appropriateness of the calibration. So on the x-axis, we have the theoretical probability. On the y-axis, the empirical probability. And we just take a look at the graph as compared to the identity function of the model-induced theoretical cumulative distribution function and the empirical cumulative distribution function. The closer this graph is to the identity, the better calibrated the model is. So this is the PP plot metric. So naturally, the derived metric works as follows. We take the modulus of the distance of the identity and this graph, and we integrate it from 0 to 1. And if we do that for a probabilistic baseline model, and we do that in a similar fashion for the Watson version 2, and we take the modulus of the area there as well, then we can in some sense compute a return, namely the return on how much the Watt-Sun system decreases relatively this area. And that tells us a visual as well as a quantitative story, and it provides probabilistic forecasts. And that is the metric which we went with. Naturally, because I enter the last minute of my talk now, there are quite a few computational challenges in that, somewhat hidden by the mathematical notation. The first is being the storage. When we talk about data which arises every 15 minutes for around 24 forecast horizons at a spatial resolution of 3 kilometers for the entire United States, guess what? We need a lot of storage. The other problem is that if we talk about a single model, which is supposed to do everything in an automatic fashion, which is variable selection, the seasonalization. I apologize for the thunderstorm in my background. The thing is, this is a computational, very sophisticated problem, so we need computational effort. So the storage problem, coincidentally, can be solved by using IBM Pairs Geoscope, which is a geospatial temporal platform. And IBM Cloud provides tools to shift a lot of this distributed computing away from the hardware locally into the cloud. And the IBM Pairs Geoscope works as follows. We can just take a look, click around, see, for example, the input data goes. And we can do the same with the inferred global horizontal irradiance, which is in pairs as well. So we can see, for example, this is the whole global horizontal irradiance, 50% quantile of California. And clicking around here, for example, provides the entire time series of the probabilistic forecasts for 60 hours in advance, 50% quantile. The IBM Cloud, on the other hand, provides a lot of features for distributed deep learning, which is required because a lot of GPUs are just required to train these large models. And deploying the model, even when it's already in existence, takes a lot of effort. So IBM provides an interactive deployment environment in the cloud. So that would summarize my talk, and I look forward for the questions. But please feel free to write me an email. It's Carlo Siebenschuh at IBM.com. All righty, thank you so much.
Thank you, Carlo. I'm going to hand the podium over to Aidan now, who will introduce the last two speakers and oversee the panel discussion. Aidan?
Thanks, Ben, and appreciate the work you put into this. Yeah, I'm Aidan Tuohy from EPRI, so I'll introduce the next two speakers, and then we'll do the panel discussion. So just another reminder on the slido.com and ESIG 8, and go in there and ask questions specific to the presenters, or ask questions we can bring to the panel and have a good discussion here at the end. I think we'll have time for a good 25-30 minutes, depending on the next two speakers. So the next speaker is Corinna. Corinna Möhrlen. Folks that have been around the ESIG workshops will know Corinna well. She holds a PhD degree from my alma mater, UCC, Civil and Environmental Engineering. Since 2003, WEPROG has been providing operational ensemble, weather and energy forecasting services, and very specialized in renewable integration. As well as the renewable integration aspects, Corinna coordinates and participates in a lot of national and international R&D projects. And since 2017, she's a board member, work package leader, and chief editor of the recommended practice on forecast solution selection in the IEA Wind Task 36, which is a great document and well worth checking out. So with that, Corinna, I'll hand it off to you.
Thank you, Aidan, for your introduction. And yeah, I'm jumping directly into the presentation. I'm going deep into an application. So I'm talking about an ensemble-based dynamic ramping reserve forecast that we have been developing together with and for EPRI in Ireland. And I want to also quickly acknowledge my co-authors, Kenneth Conway and Shawnee Griffin, and James Ryan, that is no longer in EPRI, but he has been a key driver of this, and my colleague Ulrich Westergaard. So just to give you a very quick, brief history of time, EPRI and has started in 2000 with developing forecasting and moving towards 5 gigawatts in 2020, and with a target of 10 gigawatts and a safe grid operation of 95% renewable energies. And right now we are at the 65%, and we have come there with a so-called high-speed shutdown tool, and the next step now for the target strategy 2025 to reach the 75% renewable energies on the grid. That requires a ramping reserve tool, and that's what we have been developing. So just to give a quick, some quick numbers, Ireland has now 5 gigawatt on the grid of renewable, mostly wind, and this makes out about 30% of the system demand. So the 65% system non-synchronous penetration on the all-iron system is really an achievement, but getting forward to the 75, EPRI has started a ramping concept, and the concept is really working in such a way that there is a ramping duty and an uncertainty associated with the ramping reserve, and that gives the total ramping requirement. And if we decompose this a little bit in what really this means, we can say that we have a static reserve that is built upon some base uncertainties and imbalances from renewables, load interconnections, and schedule plans. And some of the peak are also going into the static reserve, but then the peak of the renewables and the load, we can say they are quite weather uncertainty driven. And this is really what the ramping reserve tool is all about, and why it is required to have this as a ensemble or probabilistic based tool. So the uncertainty or the background for the uncertainty in Ireland is has two sources. There is a large scale uncertainty source, and that's really the storms propagating over the Atlantic from west to east with a high uncertainty growth rate of when they happen, and a kind of an information lag. We have very sparse measurements over the Atlantic, and that brings a lot of uncertainty when and how the wind is ramping up and the generation accordingly. So this is a typical winter situation. You can see two low pressure systems just after each other, chasing each other, and that's a typical situation. But then we also have in Ireland small-scale uncertainty sources, the baroclinic and barotropic instabilities that are vorticity graded and dependent on temperature and pressure. Also the symmetric or slantwise convection is a big issue on in Ireland, where we have upward displacement of air parcels, and instabilities, of course, from the sea-air interaction. Ireland is an island, and we have a lot of cold air over warm water. And then not to forget is that the growth rate of renewables penetration that at some stage also limits the available capacity or the reserve for mitigation actions. So when we bring this now into a ramping tool, then we can say the unstable weather conditions that trigger instability mechanisms, they are really responsible for that. We come from high predictability areas in the forecast to low predictability areas. And the very low predictability, that's those noise that that is carried or that is taken from the primary reserve, but everything in between that, this is where the ramping reserve services is needed. And here is an example of such a typical forecast in Ireland. You have high predictability, low spread on the forecast is the power, and then at some stage we ramp up, and then the uncertainty increases and the spread increases. We can see this, and the dotted line, the black line here, is a measurement, so it goes really up into the upper percentiles of the uncertainty band. While it's then on the next peak here, it stays down. So it's really those instabilities, and it's dependent on the weather conditions, whether we hit into the uncertain areas or we don't. So just to show you a little bit more and give you a bit more overview of how what we mean by the uncertainty, I have brought here a plot with a potential power in the background colors, and you can see Ireland here. This is a short-term forecast, and these are day-ahead forecasts from 3 of the members that we run. And you can see these sharp gradients that fronts come with, and the dots here are measurements. And when they light up in the correct color, this is when the forecast is doing good, and the measurements follow what is happening. But what I wanted to bring to your awareness is even though the fronts look quite similar on the forecast, it's quite a bit different when you look on the short term. And then here I have a plot where you can see the different clusters in the penetration where the wind farms are located. So we have a cluster here in the southwest and in the southeast, and then 2 clusters here in the northwest, and quite few wind farms in the middle. And all of these areas here are quite complex terrain, and then they are exposed to the Atlantic. So the small errors in sharp fronts and the fast moving lows really cause a lot of errors, and the uneven distribution of wind farms. Thus, the next uncertainty problem, and then we have a lot of small scale errors or uncertainties from the complex terrain here. So it's a quite challenging situation, and in 2019 EPRI launched a study, and we found out that the system really has continuously ramps up and down, and there is really very seldom wind speed that are constant over large areas, and the variations kind of in the winter time are between 16 and 27. That's why I said we needed a high-speed shutdown tool first before we went into the reserves. But what we find now with the climate change, that we see these wind speeds here all over the year. And so there is no, it's not so much in the summer, but it's still there. And the density of the capacity varies, and that will continue on, thinking about that we double the penetration over the next 10 years or 9 years. That's going to be just a matter of fact. So the challenges are really the exposure to the Atlantic, the high penetration with the 30% demand, and going from 65 to 75 safe grid operation in an island grid, that is really challenging. So to maintain system balance, also economically reasonable, there is really some kind of different forecasting required. So we need the 2-hour horizon short-term forecast, but also dynamic allocation. And it becomes really now an optimization problem of forecast error balancing, rather than looking onto small improvements of the forecasts. And so the answer that EPRI came up with is ramp reserve products. So they have developed 3 ramp reserve products. They are called RM1, RM3, and RM8. And what that really means is that that's the ramp up time. So it's 1 hour, 3 hour, and 8 hours, and the 1 hour then runs up to the 3, and the 3 runs up to the 8, and the 8 runs up to 24 hours. So from 1 hour onwards, there are different products available to solve the ramps. And to bring this down in a schematic, and if you remember the decomposition from the start, then we can say we have here the static reserve, and this is what I call the low predictability that is covered by the primary reserve. We can't really do much about that, but where we can optimize is to have this spill, to not have this spill, so reduce the spill, and then also take into consideration that a ramp up and ramp down is not symmetric. So I won't have time to go into the relationship between the ramping and reserve and all this decomposition and how the algorithms work. But so I have, there is a paper, a conference paper, and a presentation that you can check out on our webpage or on the IAA wind forecasting webpage is published there. What I want to bring to your awareness is that the optimization problem at the end for the reserve is really that we have the largest single point of failure, and then the other part of this is really the load, the scheduled and non-scheduled load. All these parts of the second term are weather dependent, and that's where the probabilistic part comes in. So the way we solve it from our part is we use 75 ensemble members. They run and they are calibrated, we can say, on the physical processes of the lower boundary layer, and should cover the uncertainty in every hour of the forecast. And we then generate percentiles that are just sorting the ensemble members, and that provides us the probabilities. And just so that you know that when we see these figures here, that's based on 75 ensemble members. And here I have brought an operational example from yesterday to today. And it's a typical up-ramping situation, but you can see there is not really very much uncertainty here. So there is none of the ramping forecast products get activated, except here a little bit. But the moment we turn over and it goes into the down ramp, some kind of uncertainty starts to happen. And that's what we can see then in the forecast. And the difficult part is then how AirGrid decides on which kind of percentile the ramp product and the ramp allocation or the reserve allocation takes place. So one thing now we can see is generating these uncertainties, and the next thing then is to decide. So now just when we go forward to the next case, to the next part of the uncertainty that we saw, I have just taken here some figures where you can see a mean in the middle here and min and max, and then I have zoomed it out here so you can see the difference in shape of the generation over the island. And if you consider the different clusters of wind farms and how different the generation looks, this is what provides kind of an overview of why the uncertainty suddenly explodes like this. And so the key findings and what this is really about is that one thing is to understand the uncertainty. This is key, and especially when we have increasing penetrations going over 30% of demand. The dynamic reserve, ramping reserve, we can say keeps operation secure and economic. And we have seen this now. We can also supplement the up-ramping with curtailment to balance kind of the security and costs. And to build this reserve forecasting tool, one of the things or the four main points that what we needed is to understand the weather conditions that generate the up and down ramp, uncertainty, the grid situations, the available reserve capacities, and the realistic load patterns that we have also heard beforehand. So to conclude my presentation, the lessons learned from 1 year of ramp reserve forecast in Ireland is that we really saw that there was a forecast paradigm shift from the deterministic to the probabilistic forecast. So ERGRID is now getting 9 percentiles for the 3 ramp horizons. And they are just kind of learning to go from static solutions to optimized problem solving. That means that, it's no longer the forecaster that has to make the decision. It's really ERGRID that is now in the planning and understanding that it's their processes that that have to make use of that information that we can provide, and that brings the single simulation point to strategic scenario analysis, and that's where we are right now, and we have seen that there is still lots to learn, and that's how I want to end the presentation. And thank you for your attention, and any questions are welcome.
Thanks, Corinna, and appreciate the presentation. That was very interesting. If folks do have questions for Corinna, please put them in the Slido, and we can get to them during the panel discussion or afterward. So we're moving now to our last speaker before we go to the discussion. Again, Bri-Mathias Hodge is well known to everyone who's been attending these meetings. He's an associate professor at the Department of Electrical, Computer and Energy Engineering, fellow at the Renewable and Sustainable Energy Institute at the University of Colorado, Boulder. He's also chief scientist and distinguished member of technical staff at NREL. So Bri's going to talk to us about some of the work at NREL today. Thanks, Bri. Bri, if you're speaking, you're still on mute.
Thanks so much. Sorry about that. And yeah, really happy to hear all the talks coming beforehand. It set up a lot of the work that I'm going to talk about today. And so I want to talk about one specific project that we've been working on for the past 3 years or so that has to do with solar power forecasting specifically, and how we can better utilize the probabilistic information that we can get from a lot of the forecasts that we've heard about in the last few talks in power system operations. And so this project, for short, we just call it Summer Go. And so it is a partnership between a number of folks. Us at NREL and CU Boulder, as well as ERCOT. Maxar provides our forecast, UT Dallas, and the University of California, Berkeley. And really, we have 4 key sort of aspects. One is developing more accurate, better calibrated, and sharper probabilistic solar power forecasts at different resolutions. The second is developing a way to utilize those in the economic dispatch sort of time period for better reliability in the power system. Third is developing dynamic reserve tools to help aid reliability in the power system as well. And then fourth is a situational awareness tool so that we can visualize those forecasts and help operators make better decisions in those fine time scales. And so, a lot of the talks thus far have talked about creating better probabilistic forecasts, and I'll do a little bit of that as well. But a lot of this I want to talk about. Okay, great, we've got probabilistic forecasts, we have better, improved probabilistic forecasts. How do we actually utilize those in order to make the power system operate more economically or more reliably? We get a great overview from Pierre, for example, just on what a probabilistic forecast is and is not. But I want to talk just here a little bit about a couple things, that we've sort of skipped over in terms of the types of forecasts and how we measure if they're doing well. This is really a tougher problem. So we've had lots of challenges with this over the years, even just with point forecasts, right? Do you use MAE? Do you use RMSE? What do you use, right? And they all have their advantages and disadvantages. But with the probabilistic forecast, really we're looking for 2 different aspects: calibration or reliability, which we saw quite a bit of earlier, And that's basically, you know, if you say something's going to happen 10% of the time, it happens 10% of the time. But the other one is sharpness. And so, you know, you want to be able to have as narrow a forecast as possible, subject to that reliability. It's really easy just to sort of take, you know, everything that's ever happened, say you're going to be in this interval, right? And that's what you see sometimes. But that's not that useful. That's really what climatological forecasts are. So, you know, looking at the literature in this area when we're getting going, it's really tough to make apples to apples comparisons at times because people use many different benchmarks, whether that's climatology, which we heard about earlier, which is great for reliability, right? Because you're looking at a huge data set, if you say it's going to happen 1% of the time, it probably does with a climatological sort of benchmark. But as a power system operator, this doesn't do a lot for me, right? You're telling me, you know, my power output is going to be between 0 and 100%. What am I supposed to do with that information, right? And so there's a number of different benchmarks that you can use, whether that's, you know, a numerical weather ensemble before it's processed, whether it's a persistence ensemble, or even a complete history persistence ensemble. So we implemented a number of these. We made these publicly available, and hopefully these can be utilized to try to get a bit more of an apples to apples comparison on what's going on. We also tried to improve some forecasts as well ourselves. And to do this, we used an ensemble-based approach. And here I'm showing some work that we use the ECMWF as our ensemble, so 51 members. And for 18 large solar sites in Texas, in the ERCOT territory, we used a Bayesian model averaging approach to try to improve it. So basically how we improved it was the numerical weather prediction models themselves were rather under-dispersed. And so they're not really getting the tails of the distribution correct. You know, if something they say is going to happen 1% of the time actually happens 10% of the time. And so that's where a lot of the improvement really comes, is in the tails of the distribution, making sure you get those extreme events right. And so this Bayesian model averaging approach was able to improve on that for all these different sites in Texas. And we compared that against some of those things that we talked about before, whether that's the raw numerical weather prediction model. You can see an example here of where it's under dispersed versus, you know, a more proper dispersion. Some basic model output statistics for ensembles, and say a 20-day climatological forecast as well. And so this has been a you know, really interesting part of the project where we've been able to improve these. And since Maxar is the solar forecasting provider to ERCOT, we're hoping that these changes will be able to go into practice here very shortly. Now, taking a step back and looking just at, you know, okay, we have probabilistic forecasts. What do we do with it? Well, as we learned from wind forecasting and just sort of power system operations over the last 10 years, a forecast is only as good as what you do with it, right? You can have the best forecast in the world. If you don't utilize that information because of your power system processes, it doesn't really do any good. And so having higher resolution on those processes is very important. Just as an example here, just looking at taking the forecast delivered from an hourly resolution down to a 5-minute resolution, ERCOT has estimated that this alone is saving them in terms of operating reserves about $6 to $7 million a year. And this is something that is essentially operational now within ERCOT. And so we have to think about not only how we're utilizing that information, but are we utilizing the most up-to-date information in the most granular fashion that we have it? And there's a lot of savings to be had just from better utilization of that information, or how you know, often we get a chance to act on that information. And so we've also been adopting not only higher resolution solar forecasts in ERCOT, but also ingesting probabilistic forecasts into the ERCOT's test system. So ERCOT already was using a probabilistic format that is a point forecast, in their case, the 50th percentile, but then also an 80% chance of exceedance, or a 20th percentile forecast. Now they're receiving all 99 percentiles within that. And so, you know, Maxar has done this by you know, implementing some of the things that we previously discussed, as well as including, you know, a much larger NWP ensemble, which helps with that under dispersion on the front end of the process. we're also working on behind the meter forecasting. Now, it was difficult to do this in Texas just because, you know, when we started this project, the distributed PV penetration in Texas was pretty small, and so hard to pick out the signal from the noise there. And so we're doing this case study on the San Diego area in California, in which we're basically taking some small representative sites that we have measurements for, and then trying to basically aggregate that up into a complete behind the meter forecast for the service territory of San Diego Gas and Electric. Another way that we're trying to utilize the probabilistic forecast information, and this has a lot to do with update rates and you know, higher resolution as well, is setting our reserves. You know, a lot of utilities set the reserves a year in advance based on basically what is climatology, right? Your historical data. And that works, that's easy. You can update it monthly, you can update it by season as well. But the faster you update that and the more recent information you update that with, the better you can do. And so we just showed some results where if we were looking at the hourly non-spinning reserve product, you can reduce your hourly average that you're holding from the current ERCOT method of about 2,300 megawatts down to about 540 megawatts per hour. So that you may think, okay, that's great, you reduce the number, and so there's an economic savings there, but what about the reliability of it? And the key thing here is you're not always reducing it. Sometimes you're actually holding more when the system, you know, if you know, in the previous ERCOT method, for example, they held to the 95th percentile of historic events. But what happens in that other 5% of the time? And so if you know one of those challenging situations is coming up, you actually want to hold more. And so while on average you can hold less and save, you know, in this case, our projection is about, you know, 77% of the total reserves over time, there are times when you're actually holding more and helping reliability as well. And that's that fundamental trade-off in power systems between costs and reliability that we always have to keep in mind. Finally, we've also implemented something that we call the risk parity dispatch, which is essentially utilizing the probabilistic information endogenously within the scheduling process. We're doing this at the dispatch timescale, so hour ahead. And so what we want to be able to do is sort of split the benefits of a fully stochastic approach with, you know, one that's more of a robust approach. A robust approach is faster, you're not considering as many sort of possibilities, trajectories, if you will. And a stochastic approach gives you, you know, a more narrow subset. You're not looking at the absolute worst case scenario at every time. And so we're doing this for a Texas system in which we've actually grown the solar penetration quite a bit. So this is based on what's in ERCOT's interconnection queue at the moment. So about 110 new solar plants, adding up to about 20 gigawatts of additional solar in ERCOT. And we're simulating the system, trying to look at how the use of probabilistic forecasts in that dispatch process would be able to provide better reliability for the system. And basically what happens is, you know, you have your morning ramp and your evening ramp with solar, which are very important, of course, because that's when you have the most change in the solar output when you're looking at a large ISO type level. And so basically what you're doing is you're projecting ahead what your imbalance will be based on those forecasts, and then you're choosing to deploy or hold additional reserves in order to counter that. So this is meant to increase the operator's situational awareness about the expected future state, and then provide them with the ability to take preventative actions, whether that's curtailment or things like reserve substitution. And you know, we've done this already for dispatch. We're extending this out to the unit commitment timeframes. And you know, this is sort of a classic duck curve problem that you see near the end of your ramp. You're starting to exceed some of your ramping capabilities. And so really, this is one of the areas that we've identified as being the most important for those probabilistic forecasts. And we're looking at ways in order to be able to, you know, basically utilize that future information to save some capacity here so that you can utilize it there at the end of that ramp. Finally, all these tools are only as good as, you know, the information being provided to the users. And so that's why we've also developed a visualization tool we call SolarView that allows users to look at the individual forecasts for different plants it's forecast like there's a and score change the time resonates together, things of that nature. And this is an open source tool that we've made publicly available already. So thanks so much for your attention. Happy to talk to you today about this project, and be happy to answer any questions.
Thank you, Bri. I appreciate the presentation and all the panelists. So I'm going to ask all the other panelists to come back on video as well, so we can kind of have a panel discussion here. Please do continue putting your questions into the Slido link. We have about 30 minutes or so left. And also upvote those. I'll try and keep the ones that get the most upvotes towards the start of the panel discussion, and those that we don't get to, I think people will provide answers after the fact. A lot of the questions are kind of one-on-one questions or individual questions. So what I might do first is just kind of start with something a bit broader. I think a lot of the presentations, probably all of them, kind of talked about the need to start adopting probabilistic forecasts, as opposed to kind of a whole lot of explanation of how people are currently using them. And we have been talking about it for quite a while. It seems from some of these presentations that we're far closer now to using those. So, as we look 5-7 years into the future, what are people's thoughts about how people are going to be, how end users are going to be using the forecasts, or how forecast providers are going to be providing these probabilistic forecasts? What improvements might be seen? What new methodologies might be used? Those types of things. And I'll start with Pierre. I'll start with you, and then we'll go through the rest of the panel. But are we actually going to be there? We've talked about this for quite a while around the use of probabilistic forecasts. Do you think in that 5-year time span we'll actually be using them?
Thank you very much. I mean, I think Corinna was giving a very good presentation in that sense, and the others too. Sorry, I point at Corinna because I really like the flow from the ensemble to visualization to trying to make sense out of it with a certain product, right? And that was the point of my presentation, is that now that we have reached this kind of maturity, that we know there's an issue, right? From the basic probabilistic information to the actual use. Now, if we're able to really design the kind of products that bridge the gap between the two sides, I think it's going to help a lot the adoption. And that's why I think within the next 5 years, what's going to happen is that all these people we saw today and others, they're going to make this connection. And that's going to take new forecast products, new visualization, or better understanding verification, as Bri-Mathias was mentioning also. So personally, I'm very optimistic, but yeah, I might be a bit biased.
I think a lot of us are. Dan, do you have thoughts on that?
Such an interesting question. I mean, I've been doing this kind of stuff for like 10 years, and we've been at a fairly similar level, like very slow progress in uptake over that time for probabilistic information. But it certainly does feel like there's more attention to it, the clients are more interested, and so on. But I think what's also interesting is the increase in demand management tools, and the increase in battery penetration is really going to make decision making quite different at the level of the grid. And I wonder, if the problem isn't going to get bifurcated into a very strong focus on really short-term information, and maybe at that level ruling out, very unlikely. Like, what can we say about what is really, really unlikely in the next hour or so? With a lot of confidence. And then, maybe also, none of us have really talked much about the extended forecast, the range at 5-6 days, and where, as we start to build a system that maybe depends on having certain amounts of building up lots of storage so that you can get through the winter peak or something. It'll be interesting to see what kind of economic decision making gets used to approach the question of, well, what decisions should we make about setting pricing, or things like that out at 5-6 days, if we're a little bit concerned that we ought to be accumulating more hydrogen in the deep underground reserves or something to get ready for the cold season.
Yeah, that aspect's definitely very interesting. Carlo, do you have any thoughts, guys?
Yeah, I'm going back to the question. So the thing is, in most probabilistic domains, conditional distributions are being generated in statistics all the time. Just that most applicants decide to throw it away and just go with the conditional mean. I feel like this is, you know, the most practical applications. I think when you go to a doctor, the doctor gives a diagnosis, and the diagnosis is inherently not probabilistic. It's not, oh, it could be 20% A, 80% B, and that's it. But it is always the model probability, and one goes with that medication. And I feel like most applicants just want, in some sense, the medication. What was previously raised by Pierre, that decision follows this probabilistic forecast. I think these models will actually range into the decision making, and I could see that there, just like there is a tendency in machine learning for end-to-end learning, is that actually the economic and system decision making will be included in these models as well, and potentially in 5 years from now, maybe the probabilistic forecast is somewhere in the second to last layer of the model, but it's maybe nice to screw it open and look into it for a bit. But I think it will go more towards the end-to-end decision making at the end.
Thanks, Carlo. And Corinna?
Yeah, I guess I would say I'm also biased, but when I started with the probabilistic or the ensemble forecasting for 21 years ago, I thought it probably takes about 10 years until we are there, and it's gone 21 years, so it's difficult to say how long it takes until it's taking off. But what I see and what is my prediction is that when system operation reaches the 30%, like we have seen in Ireland, when there is 30% of the demand coming from renewables and you're not very well interconnected, this is when the problems really start. And this is where the uncertainty in the generation from wind and solar are getting too expensive to have static reserves. And the forecasts quality and the uncertainty changes from time to time, and it's just getting too expensive. So I think the money will rule out that we can't go that route. So we have to get uncertainty and probabilistic forecasting into the applications. And as all the others have said, we have a lot of tools available now, and it's about making the end users understand how to use them. And we have gone through this process with AirGrid, and it was really a learning process for both them and us, because we always ask we can do this and this and that, but what do you want? And they said, we don't know. It's this chicken and egg problem. Like also Carlo said, you have so many possibilities, and then the end users have been used to say, well, provide me with the best you can, but the forecast paradigm changes because there is no best thing. It's about balancing the thing, balancing and cost and security, and therefore I think we can get around it. But whether how long it takes is probably dependent on how fast we get the penetrations up.
That makes sense. Bri, any thoughts from your studies?
Sure. I think the question really is, used by whom, right? And we have a lot of focus here on sort of utility ISO operations, right? But I really think it's a lot easier to get adopted more at the individual generator first. There's a little bit less going on there. I think we're going to start seeing a lot more of that. I think we're seeing quite a bit of that already, but I think that's going to sort of precede things. System operators have a ton on their plate, and so you have to make it easy for them to utilize information. So that's where really I think the two factors are. One, sort of as Pierre mentioned, you have to give them the tools to be able to utilize that information and do so seamlessly. And as Corinna mentioned, they have to have the need, right? It has to sort of hurt a little bit before they're going to do it. And so as we reach these higher penetrations, that's when I think we're going to start seeing it at the ISO utility level. But I think we're already seeing a lot of these already at the generator type level.
Makes sense. Yeah, especially with the prevalence of hybrid resources and things, I can see that happening here sooner than later. So I'm going to ask some of the questions on Slido here. So some of them are more specific for individuals. I'll just start with the ones that are most popular and try and get at least one question for everyone. Corinna, and actually this might apply for others as well, but in other regions, but how does AirGrid translate the uncertainty forecasts to the actual reserve capacity that's online?
Yeah, so they don't translate that, we do that for them. So we generate the basic forecast, and then we translate that into required reserve capacity for the three horizons, and then we provide the percentiles, so they can, their choice then is to choose which probability they want to have, which percentile they choose. What do they want to have, a 10% or 80% security level? But this is still something that is quite important, because they have been used to get one value of the kind of the best, and now they can really make strategies. They can make strategies of what they have available on reserves. They can make strategies on how secure and how economic they want to, and that's why I said in the ramp up they have the possibility of curtailment, so they can balance between cost and security by saying, okay, if curtailment is cheaper in certain situations, we curtail rather than having too much reserve running, and that's kind of the big learning that they get the end product in provided with probabilities to then choose and make their strategies.
Just to follow up on that, so have you seen them change the percentile they're using day to day?
Yes.
Okay.
Well, they don't do that day to day, but they have kind of they have made internal strategies on when they use which kind of percentiles, and they are still learning on that. So it's an ongoing process, and that's why I said, we have been running for a year now, and it has been quite successful, but there is still lots to learn how to translate this then also for the operators. So they started with very strict rules, and then they started to say, how can we relax on that, and in which weather conditions and ramp up and down can we do this differently? And that's where they work continuously on improving, and in that way also economically making the best product or the best decisions on with still keeping the security level high.
That makes sense. I don't know if others have thoughts to add to that. I know like Bri, this seems to be similar enough to some of the stuff you guys are doing around how you translate uncertainty, if you have any other comments there.
Yeah, I mean, I think as Corinna mentioned, giving the operators the ability to choose essentially their risk comfort, right? So the risk tolerance is an important aspect, and so that's something that we've tried to bake into that as well. My opinion is that the more often you're able to switch that based on the rest of the prevailing conditions, the better results you'll have with that.
Makes sense. I see Pierre has his hand up there as well.
Yeah, I just had a quick comment, because there's a bit of a common fight, you could say, between the probabilistic stuff and machine learning, and that links to what Daniel was showing in his talk. Many people have been having issues with some very advanced machine learning tools because it lacks interpretability. And I think it is the same issue with probabilistic forecasting. People, practitioners, or users, they have difficulty understanding why now this becomes the right decision with all this probabilistic stuff. And so actually, I think it's a more general issue that we have, that we need to do better work and more work in making sure that people understand, why this becomes the right decision, either because of probabilistic stuff or, very advanced nonlinear machine learning stuff. And there's a lot of efforts to do. And I think both Corinna and Daniel, and everybody, I guess, is going this direction with very low level tools, sometimes visualizations, it's not crazy to do. But then there's also some new tools from math that is like this Shapley values that Daniel was mentioning. So I think it's a general, I'll say, fight that we have, that we need to improve this interpretability of these new tools we are pushing.
Makes sense. Any Dan or Carlo, any comments? I don't think you might have.
Yeah, I was just going to compliment in that respect, compliment Bri's chart on, showing the relative skill of a bunch of different approaches. That was a really helpful a little four panel chart there with climatology versus this method, that method, showing the same forecast and a couple of different probability distributions. I think we need to get that getting better at just demonstrating what it means to have a good probabilistic forecast, getting better visualizations of what the difference between sharpness and reliability is, for example. That's really going to be helpful in getting people to have an intuitive sense for what we are telling them when we're giving them a probabilistic forecast. I think one of the toughest aspects of this, I think, is that the most useful kind of probabilistic forecast is often one that's at the tails of the distribution. We're ruling out, it's really unlikely that thus and so will happen, but those are exactly the forecasts that are legitimately the hardest to judge their accuracy, because they're forecasting rare events and you need many years maybe of good data in order to convince someone that the skill at the tails of the distribution is any good at all. So there's a couple of different hurdles to get over, both perception and understanding, but also the truth of how good the forecast can be expected to be.
That makes sense. Carlo, any additional thoughts? Yeah.
I think one thought I have after all these talks is that it seems to me that going forward, the focus of applicants and researchers alike seems to be in the tails of the distribution. So I can very well see that most clients don't even want to see the whole distribution. They just care for the extremes. So I think that for the next 5 years, there will be more of a look towards extreme value theory and actually providing consistent thresholds for whatever decisions are coming forward. Regarding the interpretability, I heard that argument a lot in machine learning, and for example, IBM is championing interpretability in machine learning. I, however, think it's kind of interesting because sometimes even the most simplistic statistical models, which actually allow interpretability, even their interpretability is thrown to the side. I mean, most simplistic example would be just simple multivariate linear regression, where nobody takes a look at p-values, nobody cares for causality or for a conditional test on independence, but then they want to have this huge model which predicts everything and nothing, and of course it has to be interpretable. So I think interpretability is a very interesting point, which is always asked for, but never really exploited, at least in my experience.
Makes sense. I go through a few other questions. Pierre, the next one has your name on it. If others have thoughts, put up your hand as well. But you gave the example of kind of the central agent, I think, towards the end of your presentation. Who would play that role? Is it a DSO, TSO? Is it others? Is there not defined?
So yeah, I was going a bit fast. I was getting pressured by Ben. There was this different use cases I was mentioning, and the first paper I wrote on this topic, I was looking at the different use cases, and actually this central agent is the agent that has the forecasting problem at hand and would like others to help with their data, right? So it can be a TSO that wants to predict, for an aggregate. It can be a DSO that predicts also for the area. That can be a portfolio manager that predicts for their own portfolio for trading. And it can be a single farm that want to use data from neighboring sites to improve their forecast. So that's one thing that not that I like, but I think is very nice with this approach, is that you can do it for all these kind of use cases. As long as you have an agent that has a forecasting problem that could profit of data of others, it just makes sense.
Makes sense.
Maybe
yeah,
I would like to make a short comment, because we have for many years in the ESIG workshops actually discussed the data issue, and And I can see that there is now, it has kind of died out a little bit because there was not really a solution. But now that we are much more digitized and digitalization is a big issue, and all the privacy stuff is kind of started to be handled. Maybe, I had for many years said, why do we not have something similar like the GTS network in meteorology, where all meteorological agencies that collect data are feeding this into a common network, and then there is access, different access from different parties that can get that kind of data out for the assimilation. And this is really what we need in the energy area as well. If we would have such a common, whether this is global or on a lower level, on a national level, this is kind of where we should be heading for. And it's agencies like the Department of Energy in the US, or in Europe it could be the European Commission or whatever, to manage something like that. And then you can get access rights to certain data, or it can be anonymized. But I think this is something that we really need to get forward and to develop all these possibilities and tools that we need for a carbon-free energy system.
Thanks, Corinna. Dan, the next one for you. What Ross was asking, have you considered the ability to forecast impact of energy prices on net load? Do you have data sets available? Is that something that's been looked at? And if others have thoughts as well, they're welcome.
Yeah, it's a good question. The load data I've been looking at is not from places that have, terribly rapid fluctuations in prices of set over time. I think, I'd be very interested in looking at. Of course, there's lots of places where price and load are, both things that you have to predict simultaneously. It's not that you can know one of them in advance. You have to do them jointly, as of course Russ knows. That also is a very interesting problem to us, and we're interested in getting into that. But we want to feel a lot more comfortable with our ability to do net load first. But yeah, thanks for the thought. I thought the obvious one would be in some market where, I don't know, a constituent component like natural gas prices were fluctuating in a way that was passed on to large consumers in a clear way from week to week. And I'd be interested in learning about markets like that, but I'm not aware of them right now.
Okay. Thanks, Dan. Carlo, this seems like it's another Ross question. The PP plot that you showed the climatological forecast showed ideal behavior below accuracy. Why is it difficult to calibrate those short-term forecasts to improve the PP shape? Any thoughts on that?
That was regarding the short-term forecast.
Yeah, that's right.
I mean, it's kind of hard because the problem is with the PP plot metric, or basically its biggest feature, that it compares against a probabilistic baseline. And just like persistence as a deterministic forecast is pretty good, in the very short run, just say a few hours, it all depends on the conditional variance one comes up with for this baseline estimator. And when the conditional variance is somewhat low, because it's, for example, a rolling average of the past observed variance in a Garch style model, then all of a sudden the probabilistic persistence is extremely well calibrated. And then even the most sophisticated model on top of that has a really hard time improving on that. However, going forward, let's say a day, usually persistence is, even the probabilistic persistence estimator is equally not able to get the probabilistic conditional distribution right. So, and that's why the very, very short term, very easily to predict, basically Dirac measure around the current state of the atmosphere, but just a few hours ahead, pretty much super challenging. So basically a technical argument for that one.
That makes sense. Any other thoughts on that? See anything there? Bri, one question came up here that I know you and I have chatted about through the DOE project. The results that you show, how easily can they be translated to other systems, or what are the ways we can do that?
Yeah, I think the forecasting specific results that we showed, those are for a number of different plants, obviously across Texas, and so different climatological zones. And so I think your mileage will vary depending on site, right? But I think those would hopefully stand up for even more diverse sites. The power system results that we showed, really the key thing is your baseline, right? To me, I feel like we're at the point with reserves that we were with scheduling, I don't know, call it 7-8 years ago, right? Where everyone was doing hourly scheduling because that's what you'd always done. And now every ISO does 5-minute, 15-minute sort of scheduling, and there's a huge benefit with that. And I think we're at that point with some of these other technologies, and we just need to sort of move forward. So I think that will be broadly more applicable. If you have a specific case in mind, feel free to reach out to me, and I'd be happy to discuss in more detail.
Any other thoughts on that question? Anything from the European perspective around how some of these kind of things can translate across different markets, different market structures?
I think most of the problems or that we solve can be also translated to others than the system operators. So, for example, the traders. We have been working with traders for many years now, and they, of course, this is where they can gain and lose on the uncertainty of what the forecast is saying, and then what the market is about to be doing. So I think it's just difficult. A lot of the traders, they don't want to be in public and tell what they are doing. So that's probably why there is not much information coming from the trading side of things. But that's also users of probabilistic forecasts. And that's going to continue on because as uncertainty increases, the trading is also getting more complicated. And I mean, there are also research projects now, and I'm also involved in some, and also applications that look into whether there should be more transparency on providing probabilistic forecasts on a control zone level for the market participants. How this can be handled and who should pay for that and so on. That's always kind of difficult, but it's at least something that is discussed in Europe.
Pierre, I saw you use your hand up there.
Yeah, no, because Corinna made a very good point. It's something I thought of before when there were some of the discussions, that we've been discussing a lot about operation, system operator, etc. But for instance, if we make a parallel to traders, I think the situation is very different. I mean, so Corinna and I, and maybe others, have been interacting quite a bit with traders in Europe, and we have many trading companies that are very mature in terms of using information and doing some optimization and trying to be smart about that. And I think just because they don't have this reliability issue, maybe. And it's much easier for them because they're in this money space only, so that makes it easier. But also it's a matter of culture. I think that they have an easier time, I think, jumping towards this probabilistic stuff. But yeah, there is another world. I mean, most of the traders with who I interact, for them, it's very natural to discuss this probabilistic stuff, how to optimally use them, etc. Yeah, I would say in that sense they are really ahead.
That makes a lot of sense. All right, we're getting to the top of the hour, so I do want to kind of wrap it up. I will ask real quick, 20-30 seconds, if you're talking to a forecast user who's not sure about probabilistic forecasts, what's kind of the number one thing you tell them they should be doing right now to start getting ready to use some of these? Maybe start with Pierre. Sorry to put this in, you'd start with, but you were the first speaker. So
what do I do in 20 seconds to convince people to play with, to use probabilistic forecast?
What's the number one thing you think they should be doing to start getting ready for probabilistic forecasts?
But something we've been discussing with Corinna, with the IEA task and with some other people, I think to design some kind of game or some kind of training exercise so that, you know, we can simulate what's going on, you know, in the decision making, in operations, in whatever, and then we start playing, you know, what happens if I have this deterministic information, what happens if I have this probabilistic information, and then since it's a safe environment also, what happens if I get the probabilistic information and I'm wrong in using it, right? And then I can learn from that. And I think these kind of things, you know, this simulation platform would be very helpful for people to just realize that it's not such a big jump towards the unknown.
All right. Just kind of training simulation, Dan.
Yeah, I think I would just say to start thinking about, you know, what are the things that you're worried about, and that's what probabilities are about, right? They're about sort of reassurance. You know, can we think about the things that I'm scared of and how I'm going to prevent them, and what kind of choices am I making, and how would those choices change depending on, you know, if I were relieved of the concern that something I'm afraid of might happen or not. Like to kind of work through your decision making process and think how some knowledge of the odds of how the forecast might be wrong would help you feel better, or you know, actually have a better outcome in your decision making process.
Makes sense. Carlo, Nathan?
I would like to reiterate what Daniel just said. Usually it's approaching a person, asking what is the specific goal here, even if it is in terms of penetration or in terms of money. Usually at one point or the other, probabilities are a tool, but since that answer is already taken, I would just argue start gambling, because then learning about probabilities is really most effective. And I think one Nobel Prize winner in physics actually argued that gambling should be taught in elementary school. So maybe that would be my proposal if I'd ever run for office.
Corinna?
Yeah, I would say the same thing as Pierre. I would say if you really don't know how why you should use it, come and join and follow us on the IEA Wind Task 36, because we are now developing at the moment our second experiment or game, let's call it game, to play, and I hope there will come another few out of the task. As we continue, and this is how you can see why you should use it.
Cool. Bri?
I guess to me the biggest thing is people do this already. They just don't realize it, right? I mean, they look at the forecast and say, oh yeah, but last week it was off by this much, so I'm going to hedge it by this, right? And so just getting people to understand that they're already doing this, and it's really not new. It's just working with better information.
All right, thanks. Okay, I think it's time to wrap it up. So I do want to thank our panelists. I want to thank Ben, the chair, for their great contributions to the discussion today. Thank all of you for your participation. It's been a fascinating discussion on the status of probabilistic forecasting across several continents. So as a reminder, we'll follow up with a written answers to any of the questions we didn't get to. I'd also like to remind you that the meteorology and markets workshops are being held, sessions are being held Tuesdays and Thursdays throughout the remainder of June. The session this Thursday is on global advances in forecasting, chaired by Jessica Harrison and MISO. Take us to Europe, Australia, and the US. No charge for these sessions. You're all invited to attend, and further information is provided on the ESIG website at esig.energy. So thanks to all the panelists and participants. Stay safe, and we look forward to seeing you again Thursday.
Thank you.
Thanks, Ben.